online classes started in the wake of COVID-19 pandemic. We at KSM College Astamkota have been conducting faculty development programs and national and international webinars on various subjects. Each of our departments has been able to get very competent speakers who have conducted very informative and useful sessions for the students, teachers, and also to public. It is highly appreciable that even during this second wave of COVID, all departments are coming forward to conduct webinars with zeal. Department of Mathematics has already conducted a 3-day webinar series this month on COVID-related theme. Last year, IQAC of our college launched its virtual platform Virtuosa 2020. As a continuation, now we are commencing its activities this year as Virtuosa 2021. Today, we are starting off the first program under Virtuosa with a 5-day international webinar series on recent trends in applied mathematics. The sessions are handled by experts of international eminence, and this will be followed by a 3-day webinar by Department of Malayalam from tomorrow, which will be an extension activity, and one by Research and PG Department of Commerce, and another international webinar by Department of Botany this week itself. Applied mathematics has attained vital importance not only in the field of technology, but other areas like life science, to which I belong, environment, climate, medical science, etc. Of late, we have seen its application in model simulations related to COVID pandemic. The theme of today's webinar, which is the first in the series, is A Gentle Introduction to Computational Complexity Theory, revealing the limits of algorithms. I am fully confident that today's session, which will be taken by a very eminent resource person, Dr. Sharma Thangachan, Assistant Professor, Department of Computer Science, University of Central Florida, will immensely contribute to PG and UG students. My best wishes for the success for this webinar series. I also take this opportunity to congratulate the HOD and entire Faculty of Mathematics. With these words, I formally inaugurate the webinar series. Thank you all.
Thank you, ma'am. Now I invite Dr. Jayashree V, Head of the Department Physics and IQAC Coordinator for felicitation. Jayashree ma'am. Jayashree ma'am. Can you please unmute your mic?
Hello.
Hi, teacher.
Hello.
Yes, ma'am. Now audible.
Hello.
Hello.
Audible?
Yes, ma'am. Now audible.
Am I audible?
Yes, ma'am.
Am I audible? Am I audible?
Yes, ma'am.
Okay, thank you. Our
Ma'am, your voice is breaking.
Yes. Dr. Mini Chandran, Dr. Savida, Head Department of Mathematics, distinguished guest of the day, Dr. Sharma Thangachan, Assistant Professor, Central University of... Okay, I'm speaking now.
Yeah, ma'am. It is audible.
Our respected Principal, Dr. Mini Chandran, Dr. Savita. That's why the break. Okay, shall I start?
Yeah, ma'am. Yes.
Okay. Our respected Principal, Dr. Mini Chandran, Dr. Savida, Head the Department of Mathematics, distinguished guest of the day, Dr. Sharma Thangachan, Assistant Professor, Central University of Florida, Orlando, dear colleagues and dear participants, a very good morning to one and all. It's a commendable initiative by the team of mathematics to organize an international webinar series lasting for the next 5 days. As the accuracy coordinator of this, I'm really glad to see that Team Mathematics has taken initiative to organize a webinar of this academic year. Actually, Versa is a common platform for webinars which we started last year. Upholding the slogan, transcending lockdown barriers through academic outreach.
Thank you, ma'am.
However, we never thought that the same situation will persist this year also. Let us hope that we shall overcome this pandemic situation very soon. I'm proud to say that the dynamic team of mathematics has
Sorry, Jayashree ma'am, voice is breaking. Thank you. Thank you, ma'am. Now I invite Dr. Regida, Assistant Professor in Department of Mathematics, to deliver the vote of thanks.
Good morning, everyone. Today, I have been bestowed with the privilege of delivering the vote of thanks on behalf of our maths department. Let me begin by expressing my gratitude for opportunity. Great honor to have with us today Dr. Mini Chandrasi, the principal of this honored institution. Your presence added unprecedented value to this venture. Thank you, ma'am, for joining us today and sharing very valuable insights. My humble gratitude to Dr. Sharma Thangachen, resource person for today's webinar. I am sure it will be a great experience for all of us. I also extend my thanks to Dr. Jayashree V, Head of Physics Department and IQAC Coordinator, for her valuable presence. Our gratefulness to all the participants who have joined us and making this program a success. Hope each one of you find this as beneficial as we had enjoyed coordinating this. Thank you all.
Thank you. Now I cordially invite Dr. Sharma Thangachen to handle the class.
Okay. Can you guys hear me, CV? Or is it all fine?
Yes, sir.
Okay.
It is visible.
Visible, right?
It's also audible, very clear, sir.
Okay, all right, good. And yeah, so it's going to be pretty informal. So if you guys don't mind, if you can keep your cam on, like I think many of your cams are off. So if you can leave your cam on, it is easy for me to see your faces and, because we all teach classes online, right? So if you don't see the face, it's very hard to say something. Yeah. Okay. Okay, everybody is welcome. Okay, so yeah, thanks again for inviting me. Especially to Savita ma'am and Dilip Kumar. I know Dilip for many years. So let me say myself. I'm as you know, I'm a professor at University of Central Florida, Orlando. I came to US in 2008, and I'm originally from Pana, Kottayam, and What else? Yeah, I studied in Calicut for my bachelor's, NIT Calicut Engineering. So I think, so probably this is the first time I'm giving a talk to a mathematics department. I have given multiple talks to computer science people, but I haven't really talked to math people much. I mean, I have been I have been doing math all the time, but this is the first time I'm meeting a fully math people. So I'm not exactly sure what topic I should have picked, but I think I picked something which is interesting for you. So please stop me and ask me questions if something is not very clear. And this is not very technical talk. All I want to explain in this talk is to show you some of the beautiful things in computer science, which is purely mathematics. Okay? So the only thing I know is mathematics. I don't know enough computer science. In my life, I haven't done that much programming. The only thing I have done is mathematics, and I have survived. So I just want to show you what all beautiful math things you can do within computer science. Okay, so that's my goal for the next half an hour to 45 minutes. Anyways, so complexity theory, this is one of the field in computer science. And in some sense, this is opposite to algorithms. And I guess all of you know what algorithms are. Algorithms are, it's something like a step-by-step process to solve a computational problem, right? Right. So that is what is algorithm. So most of us know what is the meaning of an algorithm, but many of you might, I mean, by you means like students, might not be familiar with what is complexity theory. It's all about explaining what algorithms cannot do. Okay. So it's all about understanding the limitations of algorithms. So it's something much more interesting. Okay. So it's not about solving. It's just to explain why we cannot solve something. So that is what is complexity theory about. Okay, so just to start with, so I have a few things listed here. The first thing is twin prime conjecture. So these are some of the math terms. So I just picked them so that these are familiar to you guys. Twin prime conjecture. Can anyone tell me what this is? If you are shy to,
Yeah.
you can, yeah.
That is the availability existence of prime which are very near. That is about 5 and 7 are primes. Similarly, what about the number of primes such as the closest primes? That is the conjecture.
Yes. Yeah. Please interact with me. Sometimes I might make mistakes, so please, help me to explain these things. Anyways, so we all know that the number of primes is infinite, right? There is infinitely many primes. But the interesting question is, what about twin primes? So twin primes are like, 3 and 5 is a twin prime. Means they are different. The difference between these two numbers are 2. Similarly, 5, 7 is a twin prime. Like 11, 13, or 17, 19, etc. These are twin primes. The question is the number of twin primes is also infinite? Okay, so that is what is called twin prime conjecture, and we still don't know the answer. We don't know whether these numbers, after some point, the numbers will stop behaving like this, right? We still don't know the answer to this problem. Okay, so that is called twin prime conjecture. People have been trying to find a solution for this for the last 200, 300 years. We still don't know the answer. Okay, so that is what is twin prime conjecture. Another thing is called Goldbach's conjecture. It is even older. I just checked Wikipedia. It is almost 250 years old, 1740s. That was the first time somebody asked this question. Can anyone tell me what this is? Goldbach's conjecture? In case if anyone remembers. Okay, it is even much more simple, okay? It simply says the following. You take any even number, which is greater than 2. Right? Any even number which is greater than 2, like 4, 6, 8, etc. It can be written as the sum of two prime numbers. Okay, that is a statement. Take any even number greater than 2, it can be written as the sum of two prime numbers. For example, 8 can be written as 3 plus 5. Similarly, 10 can be written as 5 plus 5. Right? 12 is 7 plus 5. This is a statement. Is it true always? Right? The conjecture says that any even number greater than 2 can be written as the sum of two prime numbers. We still don't have a formal proof for this statement. Like all the numbers with computers, we have checked almost, so many numbers, billions, billion, multi-billions. And we have seen that we can write pretty much any number like this, but we still don't know if this is how it is when we go to infinity. And that is what is Goldbach's conjecture. All right? And there is something called Raymond's hypothesis. I guess you know better than me this thing. Okay? Again, we don't have an answer to this. Nobody has proved, right? Nobody knows the answer. There is some statement, we don't know whether it is true or false. It is unsolved. So this is unsolved, this is unsolved, this is unsolved. And have anyone heard about this problem, P versus NP? This is another problem which is also unsolved. And this is very important too. For computer science people, this is very important. Okay, board is not clear. Okay. Okay, is it clear, board? Like, I'm following the chat. Somebody said that board is not that clear. Is it all right now?
Yeah, I'm okay with that. I think I feel it's a please pin that is Professor Sharma's screen, then that is screen, then it will be a full screen.
Yeah, my
Okay.
screen will. You have
Yeah,
to on my screen, so that way you will see.
Yeah.
So that way you can see. Yeah. So this P versus NP. Has anyone heard about this problem, P versus NP?
There is a time that takes to solve a problem, like polynomial time and non-deterministic polynomial time.
Yeah, thank you. So this is another important problem. It's called P versus NP, and that's what I want to focus today. At least I just want to introduce this problem to you guys. It's very important for computer science people, and it's still open. It's still open. We don't know the answer to this. The question is whether P is equal to NP or not. And something cool about this problem is if you can solve this problem, you will get a prize. You will get a cash prize, which is $1 million, 1 million Canadian dollars, which is almost like 5 crore rupees, 6 crore rupees in Indian rupee, right? So that is what is this problem, okay? All right. Yeah, so my focus is to, explain a little bit about this thing today. And this is one of my favorite subject. I teach this in my classes. Okay. So what I have explained here is like 4 problems. All of these are open. We still don't have a solution. Now, the interesting question is, people have been trying to solve this for many years. What is the reason, why we are not able to solve these problems? Right? The question is, these problems are 200, 300 years old. And so many smart people have lived, right, before us. And they all tried and failed. Right? So one question I can ask you at this point is it because we are not smart enough to solve these problems? Or is it because there is no solution for these problems? Am I clear? So is it because to find a solution, right? This is a problem, and to find a solution, at the first place, there has to be a solution, right? Then only we will be able to find it, right? To solve a problem, there has to be a solution. So my question is,
No, we can solve. We can prove that there are no solutions. That also is possible. In certain cases, that has been done.
yes, so we can prove that we cannot solve our problems, right?
Yeah. That's why it's possible.
Yes, that's where I'm going. That's where I'm going. Okay. Yes, thank you. Yeah, so there are some, at least there are some big theorems which says that we are not going to solve all problems in this world. And do you remember what that theorem is? Or at least, like, what is that statement like? Who came up with this? So there is a famous theorem. There is a famous theorem. At least you guys should know better than me. It came from mathematics. It's not computer science. Like at the time when these people were coming up with these theorems, computer science was not even born. So there is something called Gödel's incompleteness theorem, right? So Gödel's incompleteness theorem says there is going to be some problems, or there are going to be some statements which might be true. For example, like this twin prime conjecture might be true, but we might not be able to solve it ever. Even after 100 years or 1,000 years, maybe some more smart people will born, but even then we might not be able to solve this. We might not be able to answer these questions, or we might not be able to come up with a proof for these problems. Okay, and that is what Gödel's incompleteness theorem says. There are going to be some problems which we will not be able to solve. All right, so this is all mathematics. This is all mathematics, and all of this theory is from 1920s, almost 100 years old. Almost 100 years old. And it is after that the computer science, started, like 1940s and all, right? During the World War time. So that was the time computer science was born. So Gödel's incompleteness theorem says we won't be able to prove all math statements. Okay, we won't be able to prove all math statements. So now what I can do is I can translate this statement to computer science, and I can ask you one question: will computer be able to solve all computational problems? In other words, see, computer is nothing. Computer is just doing something faster, right? See, it will just, whatever we say to do, it will just do it much faster than us. That's it, right? It might do it 1 billion times faster than us, but that's it. If we cannot do this, then computer also won't be able to do that. It might take 1 billion years for us, then computer might do that in like 1 day. But if we cannot do that in 1 billion years, computer will not be able to do at all, right? So I can ask this question: will it be possible to come up with an algorithm for all computational problems? And the answer is no. Okay, so there are going to be some computational problems for which we are not going to come up with a program. We are not going to come up with an algorithm. An algorithm is what? It's just some step-by-step process which we can apply on an input to get the output. That's it, right? So, input So these are some terms I just want to introduce. There is going to be a computational problem. There is going to be a computational problem. For example, finding the shortest path, right? Finding the shortest path. I will give you a graph, and I just want to go from one place to the, from a source to a destination. We use it all the time, right? In Google Maps and all. So that is a computational problem. So the input might be a graph and a source vertex, and I want to find the shortest path. right? That is the output. And the algorithm is nothing but the steps you need to perform on the input so that you will get the output. That's what is an algorithm. So the question is, will I be able to come up with an algorithm for all computational problems? The answer is no. But as of now, I just told you in an informal way, right? In an informal way. I just want to show you a slightly more formal way why we cannot design an algorithm for solving all computational problems. And the way we're going to prove this is using just math. So all the time we're going to use math. Okay? So in math, okay, how to start? All right. So these are some terms you know you are familiar. There are two types of set. One is finite and the other is infinite. And once we get into this infinite business, things get more messy, right? So once we get into set, there are two types of set. One is finite. So finite is not interesting because once it is finite, we can do anything. Now the next is infinite. But within infinite, there are two types of sets, right? One is countable and uncountable. So that is something which you are familiar, right? Countable and uncountable, right? There are two types of sets. All right. So what I can do is the following. And you know that uncountable is like, much larger than countable, right? So what is the meaning of countable? Countable simply means we can list them, right? We can list them, we can count them. So in other words, to understand what countable means, so let me just, like whenever we want to compare two sets, right? I just want to recap. I think you know this, but still I just want to recap. So let's take the set of all numbers, 1, 2, 3, all positive numbers. So this is a countable set, right? Now if I take the set of all even numbers like 2, 4, 6, 8, this is also countable. And we say that both are countable and both are equal, right? This is what we say. But how do we say it is equal? We are not going to compute its size. We don't compute its size, but what we do is we kind of come up with a mapping between, a one-to-one mapping between the elements in this set and this set, right? That is how, without even figuring out what is the actual size, we have a mechanism to say that both sets are of the same size. It's almost like this. If I ask you this problem, like in this world, what is the total number of husbands and what is the total number of wives? Are they equal, right? If I ask this question, like in marriages, in like proper legal marriages, like male-female marriages, what is the total number of females? I mean, if I ask this question, like, is the total number of females, married females, is the same as the total number of married males? We know that they are the same, right? Without even knowing what is the total number of married men or what is the total number of married women, we can say that they are the same. All we are doing is like a one-to-one mapping, husband, wife, or spouse, right? So it's the same thing. So countable. So this is what is countable. And whenever we cannot come up with such a mapping, they are uncountable. Now to prove that there is not going to be an algorithm for all problem, all I have to show is the following. I just want to show you only one thing. The number of problems in this world is uncountable and the number of solutions or algos is countable. If I can show you this, we are done, right? Make sense? if I can show you that the number of problems in this world is uncountable, but the number of solutions I have is only countable, then in some sense, there are more problems than the solution, so some problems are not going to have a solution. Like roughly, this is what I want to show you. Okay, now to just get into more formal things, it's still not very formal, like kind of informal. This is a technique. So let me just take a function. Function goes from n, where n is a set of four, natural numbers, to 0 and 1. 0 and 1 means in computer science true or false, right? So, how many such functions are possible? Is the number of such functions countable or uncountable? The number of functions.
It is countable because
Number
it's
of
a subset of.
functions.
It is countable because it's a subset of the cross product of n and 0, 1. It is countable.
It is countable?
Yeah. Why not?
Uncountable.
How?
The number of such
Number of-
functions.
Sorry, I need a bit more clarification.
It's number of functions.
Yeah, number of
Will you
functions.
take the card like you
A function from n to 0, 1 is a subset of n cross 0, 1.
Number
So
of,
it is 2 raised to cardinality of n cross 0, 1.
yeah, 2 raised to cardinality of n. Is that countable?
Yeah, n cross 0. Yeah.
Yeah, 2 raised to,
Yeah.
yeah, that I agree, but that is not countable.
2 raised to.
2 raised to infinity is not countable.
Oh, so yes, yeah. Sorry.
Yeah.
You are right.
Yeah, so what I can show you is the following. It's a very simple thing only. Okay, suppose I'm going to prove this using contradiction. All right, I'm going to prove this using contradiction. So contradiction means what? I can list all the functions, right? I can list all the functions. Like the first function is f1, the second function is f2, the third function is f3, f4, etc. These are the functions. Okay, etc. These are the functions. So what I'm going to do is I'm going to show you a matrix. It's like exactly diagonalization. Have you heard this word? Diagonalization, Cantor's diagonalization, the same thing. Okay, so I'm going to write these numbers here 1, 2, 3, 4, 5, 6, 7, 8, etc. Now f1 is a function, it's a first function, and I'm going to just write what is the value, 1 or 0. Is it 1 or 0 with respect to? For f1, is it when input is 1, what is the value? 0 or 1? We just write whatever is the answer, okay? Let me assume that this is 0. And for f1, 2 is whatever is the value, you just write it down. But maybe it is 0. F1 is 1, maybe 0, 1, etc. What about f2? Like 1, 1, 0, 1, 0, etc. F3 is maybe 0, 0, 1, something like this. Okay? So all I have done now is I just wrote all the functions. I am assuming that this is countable. I'm going to come up with a contradiction. So if this is countable, I can list them. These are numbers, natural numbers 1, 2, 3, 4, etc. And all I am writing here is what is the value of f1 when the input is 1? That is, let me just take it as 0, like this. All right. Now, all I'm going to do is the following. I'm going to come up with a new function. Okay? I'm going to come up with a new function. Let me call it as f star. is a new function which is defined as the following. F star I is equal to is
0 if
F what is that?
IFI is
Oh yeah, FII is 1, right? So I just created a new function. It's, and all I'm doing is just Cantor's diagonalization. Okay? I just created a new function, and as you can see clearly, this is also a function which goes from n to 0 or 1. Right? So now if the set of all such functions is countable, then this function has to be one of these functions. This function has to be one of these functions. And clearly, this function is not f1 because you can see that this function and this function are different when the input is 1. See, when the input is 1, this function is 0. But this function will give 1. We're like switching them. So all I have done now is I just created a new function which I cannot fit in here. Therefore, my first argument that this is countable is wrong. Okay, so essentially the set of all such functions is not countable. Okay, set of all such functions is not countable. Now, what I originally wanted to prove was the number of algorithms, right? The number of algorithms is countable and the number of problems. So here as a problem, what I'm taking is the following. Here as a problem is the following. I get an input, then I have to compute something, and I need to get some output. Here I'm just considering only those problems which are something like a decision problems, like either 0 or 1. See, even if I show that the number of decision problems are too many, my job is done, right? Like even a subset is uncountable, then the whole set is definitely uncountable. Okay? So the number of functions is uncountable. Okay? The number of functions, I mean, that is what we want to compute. So therefore, the number of problems is uncountable. The number of algorithms. An algorithm is what? It's just like a text, step-by-step process, right? Which we have to do. And the step-by-step process, we can just write it down on a piece of paper. And we can convert that to a binary string. Like on computers, everything is binary. And once it is a binary, it is just a number. And that is a number. That's a number here. And these numbers are countable. All right? So all I want to convey was the number of problems is uncountable. The number of solutions is countable. Okay? So this is the first thing we learned in computer science. This is called, intractability and all those things. So we learned that there are going to be some problems which we cannot really solve. What's the time? Are we good with the time? Okay. Please stop me if I'm going too much. And now I just want to give you some solid examples for some real computer science problems which we cannot solve. And one such example is, if I give you two programs, and if I ask you, are these programs the same? Okay, I'll just give you two programs. The two programs might be doing, like, for example, so let's say, let me just take two programs, okay? So program one, like input is let's say x, y, Then you, let's say, create z is equal to x plus y and output z. So this is a program which takes two numbers as the input, sum it up, and give it as the output. It's so simple. So this is one program. And another program is program 2. Input is, let's say again, x plus y, and z is y plus x, output z. Okay, so you can see that both are the same program. Both are the same program. Right, these are easy examples, but in general, no, you cannot design an algorithm that will take two programs as input and decide whether these programs are the same or not. When I say same, I don't mean matching line by line. Right? Line by line can be different. Like, for example, like instead of input as A and B, I can even give input as like A, B, and A plus B. It's again the same program. It's again the same program. Right? These are the same program, but will I be able to come up with a bigger program, like almost like a super program or a mother program that will take two programs as input and tell you whether these programs are the same or not? We will not be able to solve this problem. A more famous problem is, if you search in Wikipedia or Google, you will see something called halting problem. So halting problem, have anybody heard about this problem called halting problem? Okay, so it's another interesting problem in computer science. It simply is the following. The question is the following. See, you have a program. A program is what? Program or an algorithm is what? It takes an input and it will just run, right? But sometimes if something is wrong with our program, this will run forever. It will get into an infinite loop or something. It will run forever. If it runs forever, it will not halt. Usually any decent program will run for some time and it will stop, right? So if I give you a program, and I will ask you this question. Now, if I feed this input, this particular input to this program, will this program halt or not? Okay? So how to answer this problem? One option is we can just feed this program to the input and just wait. Right? So this program will keep on running. It will run for 1 minute, 1 hour, 1 day, maybe 1 month. But even after 1 month, we don't know whether it will halt. Maybe we can wait for 1 year, 10 years. But if it doesn't halt, we cannot answer anything, right? If it halts, we can say that it halts. If it doesn't halt, we don't know how long to wait for. Right? So that is not a good option to halt or not. Now the question is, can I design another program that will take can I design a new program, like a very strong program, that will take another program and another input, and an input as the input to this program? Now this mother program should tell you whether this input program will halt or not for that input. And what we can prove, again using diagonalization, is that we cannot come up with such a program. That is called halting problem. And all of these are done by one guy called Turing, Alan Turing. Okay, so I should not write his name. So Alan Turing, this guy lived in almost 100 years back, right? In 40s, and during World War time, he broke the Enigma mission and all. There is a movie, Imitation Game, right? Imitation Game. There is a Hollywood movie. You know, if you haven't watched it, you should check that out. Yeah. So he is the most important figure in computer science, and that is a guy who came up with all these fundamentals. Okay, so now let me go towards P versus NP. So what we have seen so far is there are problems. There are many problems in this world, I mean many computational problems, and some are solvable and some are unsolvable. And there is no point in worrying about unsolvable problems, right? Once we prove that this is unsolvable, we can forget about them. Right? Because there is no solution, so we don't need to worry about it. We are not going to be successful anyways. So let's forget about all the unsolvable problems. Now we have to worry about the solvable problems. So once we are in this solvable domain, we want to ask this question: how nicely or how efficiently we can solve it. Right? So now we are worrying about only those problems which we can solve. So let me just let's take this simple problem called sorting. So sorting is perhaps the most fundamental problem. I give you a bunch of numbers and I just want to arrange them, right, in the ascending order or descending order. So that is what is sorting. And sorting is a problem which we can solve very efficiently. Right? Even the stupidest algorithm is like, just go through all the numbers, find the smallest, put it at the beginning, then go again, find the second smallest, right? Go again, etc. So at least we can solve this in quadratic time. And if you do something more smarter steps, we can solve it faster. Okay? So sorting is easy. It's easy. What about shortest path problem? So shortest path problem is the following. You are given a graph, let's say G, B, E, and you are also given two nodes, let's say source and some destination, two vertices, and I want to find the shortest path from S to T. That is called shortest path problem, or more specifically single source shortest path problem. All right? And again, this is something which we can solve efficiently. Actually, we can solve this in roughly V plus V time, very close to V plus E time. Okay? There's a big O in front of that. Big O notation, big O means like simply just get rid of all the constants, okay, intuitively. So this is something which we can solve in close to linear time. The time you need to solve this problem is proportional to the size of the input. Now I want to mention another problem, TSP. TSP, I think, traveling salesperson. So traveling salesperson is what? I give you a graph, right? There is some, all the edges have some weights associated with it. And I want to start from a node and I want to essentially visit all the vertices and come back by traveling the minimum distance. That is TSP. All right. So how efficiently can we solve TSP? So anyone knows this answer to this? So what is the easiest way to solve this problem, TSP? I give you a graph, right? Again, graph. Let's say n vertices. And I want to find a tour and come back to the place, like original city. It's almost like, we want to travel from like, maybe Trivandrum or, and visit all the capitals of all the states and come back or something like this. Okay, assuming that we are flying like direct flights or something, and we want to minimize the total distance or cost or something like that. So the easiest way to solve this problem is just try out all combinations, right? If there are n cities, we can just enumerate all the n factorial ways of traveling, right? Then compute the distance, the total distance corresponding to all of these n factorial options, and pick the minimum. That is a straightforward solution. And unfortunately, that is pretty much the best we know as of now. Okay, that is pretty much the best we know as of. I mean, there are slight improvements, but not too much.
This is called critical path method.
Sorry?
This is called critical path method, CPM.
Critical path method.
Oh, there is an algorithm or something? Oh, okay. Is that a solution? I mean, I don't know actually. That is the algorithm to. Is that the algorithm or? Sorry.
Yeah, algorithm is there, CPM.
Oh, okay.
Used in operational techniques.
Oh, is it? Okay. So what is the complexity? I didn't.
It is more like a scheduling problem. So it's like scheduling the jobs. Similar to that, when it comes to paths, we look at the weights of the paths and try to see how we can schedule it. Something similar to that.
Oh, okay.
So the complexity will be in aligning to those scheduling algorithms and things like that.
Oh, okay. But still, the worst case is going to be something like this, right? It's going to be exponential, right? The worst case. It has to be. Otherwise, something is, yeah. So it's going to be like too bad. Like instead of n factorial, you can actually get it something like 2 raised to n or big O of n. But that's the best we know as of now. We don't know anything better than that. Okay. Yeah, I don't know about the critical path method. Sorry. So, but anyways, this is what it is. So TSP is a hard problem, and yeah, enumerating is one option, and the best algorithm we know as of now is probably slightly better than that, but not like n square or in fact not like n square n cube or anything. Not polynomial. It's almost exponential. Okay. And there are so many other problems, for example, like click problem. So click. So click problem is what? It's almost like I give you a graph, and I will also give you a number, something like, let's say G. I will also give a number, let's say K. And now I ask you, is there a complete subgraph within this graph G? So is there a complete subgraph of size K? That's what a click means, right? A click is, right? A click of size K simply means you want to find K vertices in such a way that they all are connected to each other. Right? That's what a click means. And the easiest way to solve this problem is you just take all possible combinations of K vertices. There are going to be n choose K of them, which is almost n raised to K. And you just check if all of them are connected. But the sad part is when K is too big, when K is close to n, that is like n raised to n. So n raised to n is like bad, right? Like more than exponential. More than exponential. So this is TSP, this is click problem, and there is another problem called partition problem. Anyone heard about partition problem? So partition problem, all I'm asking is the following. So suppose, imagine that, let's say there is a, let's say your parents, or let's say your daddy wants to, partition his property among two of his children, but he wants to partition them equally. he has n properties, and each of the property has some values associated with it. Okay, and he want to partition this n properties among two of his kids in such a way that the total value of these properties, total value of all the properties given to both children are the same. It simply means I give you n numbers. Can you just partition these n numbers into two sets in such a way that the sum of the numbers in both sets are the same? And what is the simple way to solve this problem? Just take the power set, sum it up, right? Okay, take the power set, like now take each element within the power set, sum it up, and check if that is equal to the total sum divided by 2. But this method again will cost you 2 to the n, exponential. So what we can see is there are so many problems where the trivial solution is 2 to the n, and we still don't know how to solve this in time better than exponential. But there is some nice property with all of these problems, which is the following, that even though we cannot solve these problems, we can kind of, if somebody solves this problem, okay, suppose your friend already solved this problem, and he comes and tell you that, okay, see, I have solved this problem, then he will be able to convince me in polynomial time. In other words, these problems are hard to solve. But suppose somebody solved this problem, it is very easy to verify that it has a solution. For example, partition problem, or let's take the traveling salesperson problem. Suppose traveling salesperson problem, there's a decision version of the problem. It simply means, is it possible to just travel all the cities and come back within so much distance, within so much total distance? If it is possible, and if somebody has already figured out that it is possible, then that person can convince me quickly that it is possible. And how to convince me? He just need to show me this is a path. Okay? So hard to solve, but easy to verify. Similarly, click problem, hard to solve. We still don't know how to solve it. But if suppose there is a solution, and then it's very easy to convince you that there is a solution. How to convince you? I just need to give you all the vertices within the click, so you can just check them. Similarly, partition. Okay, so this is a common property. Now, an important question, which is P versus NP, that's the first thing which I started saying, is the following. Are all the problems that can be verified in polynomial time can also be solved in polynomial time? That's what is P versus NP problem. So are all the problems that can be verified in polynomial time can also be solved in polynomial time? That is P versus NP. Okay, and it is still an open problem, as I said before. Once you solve it, then you get $1 million. So Dilip, how good are we with the time?
Yeah, I can, pardon?
Are we all right with the time?
Yes, sure.
So this is all I wanted to say about like P versus NP. And now I just want to convince you, I just want to explain some of the latest thing happening in this area. Okay? Just like an overview. Uh, So, by the way, these are problems that needs exponential time, and there are problems that needs even more time, more than exponential. And I'll just give you one example. It's about chess game. Okay. So suppose two people played chess. Okay. So they have played up to, up to some steps. And now at this point, I'll give you a snapshot of how the keys are arranged on the chessboard. Now I ask you this question. From this point, is it possible for the first player to play and win the game? Okay, two players are playing. They have played up to some level. So now, now you have an arrangement of the keys in the chessboard, and I give you the snapshot of this arrangement. Now the next movement is the first player's movement. And I'm asking, is there any way the first player can play from this point? Like, is there any way that he can play from this point and win the game? And this is something which is even harder than all of these problems. When I say harder, it needs more resources to solve. All right? Okay, so all the things what I have said so far is like pretty classical, 50 years old topics. And some of the latest things, what is happening in this area is called it's called fine-grained complexity. Fine-grained complexity. So previously what we were doing was, I give a problem, for example, let's say TSP. Now the question is TSP in poly category or more than poly, right? Can we solve this problem in polynomial time, or is it something like NP complete? So NP complete essentially means it's like kind of exponential. We still don't know if it is exponential, but this is the best we know as of now. Okay, so this was the game before, to categorize between poly and non-poly. Now the latest game is called fine-grained complexity. Now there are some problems which needs polynomial time, like n or n square, n cube, etc. So all of these are polynomials. Now can we prove that these problems actually need n square time or n cube time, so on and so forth? So it's more fine-grained. Previously, the separation was like either it is here or here, like polynomial or exponential. Now it's like we are within this polynomial hierarchy. So is it like n square or n cube or n raised to 4? This is where we are. This is what is happening now. And some of the recent breakthroughs are, for example, alignment problem. Some of the recent breakthroughs are alignment. So alignment is a problem in biology. Okay, it's similar to edit distance. So edit distance problem is the following. If I give you two strings, and suppose you are allowed to make changes in the first string. By changes, I mean you can actually insert a new character or delete a character or substitute a character. These are the edit operations, standard edit operations. So what is the minimum number of edit operations you need to do on the first string so that you can convert that to the second string? That is called edit distance problem. Okay, and alignment is a more general version of edit distance. So when it comes to two DNAs, right? When it comes to two DNAs, our DNAs are simply strings. Like a human DNA Well, it's essentially a string of like 3 billion characters, 3.2 billion characters. Now, if you take, your DNA and your another human's DNA, you are almost like 99.99% the same, which essentially means the edit distance between you and another human is very small. Now, if you compare your DNA with your parents' DNA, if your mom's or dad's DNA, it's even more closer. That means the edit distance is even smaller. Okay? So one of the interesting questions was, if I give you 2 strings, how quickly can I compute the edit distance? And the best algorithm we knew, it's a simple dynamic programming algorithm. The best algorithm we knew was taking n square time. This was known for like 50 years. Like, it's an easy textbook algorithm. And people tried to improve this, but no one was successful. But now we kind of know that most probably we are not going to break this bound. Because using this fine-grained complexity, it's again like more math. We can somehow prove that this is very close to the best we can hope for. Okay, I just picked edit distance as one example, but there are so many problems like subgraph isomorphism, subtree isomorphism. No, subgraph isomorphism is, I think it is incomplete. There is something called subtree isomorphism. If I give you a tree and if I give you another tree, will it fit somewhere here or there? It's called subtree isomorphism. That needs n square time, and we can prove that also needs quadratic time. And it is actually one of my result. And I have also done few things around this area. Yeah, pretty much that's all I wanted to say. If you have any questions, I can take from this point. Any general questions? I know that this was probably a bit hand-wavy, but yeah.
What is the meaning of saying that a problem is NP hard? NP hard.
What is the meaning that a problem is NP hard? Okay. Okay. I can explain quickly. There are a few terms. One is P, one is NP, one is NP hard, one is NP complete. So P is very easy to understand. So P means solvable in polynomial time, which simply means n raised to c for some constant c. That is polynomial. NP means, NP has like the real meaning of NP is solvable in polynomial time using a non-deterministic Turing machine. It's weird, but which actually means you can verify it in polynomial time. Polynomial time verifiable, that is NP. Now NP hard. Okay, so NP hard all right, so to explain NP hard, okay, let me introduce one more term called polynomial time. polynomial time reduction. So polynomial time reduction simply means the following. Let's take two problems, let's say A and B are two problems. And if I write something like this, okay? If I write something like this, the meaning is A is poly time reducible to B, okay? If I write something like this, its meaning is the problem A is poly time reducible to B, which means the following. If B is in P, which implies A is in P. Means if B is solvable in polynomial time, then A is also solvable in polynomial time, which essentially means B is something harder than A. B is at least as hard as A. That's what the meaning of this term. Okay? Now, NP hard is I'm giving a rough meaning of NP hard. A problem if A is NP hard, then does it make sense? So NP hard is essentially like, very hard problems, like very, very, very hard problems. Okay, very, very, very hard problems, which we don't know even.
Sir, my question is, what is meant by this hard? I was asking this question so many times to computer science people, and they didn't give a satisfactory answer. Being a mathematician, I think you can. What is the meaning of saying that the problem is hard?
What is the meaning that the problem of saying is hard? Okay. So essentially, in computer science, if we can solve that problem in polynomial time. Okay, so usually we use n to represent the size of the input. Okay, n is the size of the input. If the problem is solvable in polynomial time, or if a problem belongs to class B, means it has a solution which runs into some constant. That is what is. And
Polynomial.
If it is polynomial, then in computer science, theoretically, we say that, okay, polynomial time solvable problems are easy problems. Theoretically, like n raised to 100 is not easy, right? It's not practical, but theoretically speaking, anything which runs in polynomial time, we kind of say that, yeah, it is easy. But the moment it goes beyond polynomial, like exponential and all, is like too much, too hard. That is how we use that word, hard and easy. Does that make sense?
Okay.
Yeah. We say that if it is polynomial, it's easy. If it is not polynomial, then it is hard. Right? That's how we kind of say this.
Yeah. Okay.
Now this NP hard, NP completeness, this is like, some theories around this. P means solvable in polynomial time. NP means we don't know if we can solve it polynomial time yet. That is the biggest question, $1 million. But these are problems which we can verify in polynomial time. Okay? We are currently talking about decision problems. And If it has a solution, we can quickly convince someone else that it has a solution. Okay? I can sit with you and I can explain you this is a solution and you will be convinced in polynomial time. That is NP. Now NP hard is something which is even harder. Right? It will definitely need more resources. Okay? It will definitely need more resources. And this statement, you can see this statement. If something is NP hard means it's a very hard problem. And what I want, all I'm saying is, if suppose suddenly, if that problem can be solved efficiently, then everything else in P and in NP can also be solved in polynomial time. That will probably get a sense of it, right?
Yes, sir.
Yeah.
NP hard is like very hard, but suddenly if it is easy, then everything else is easy. Now the last thing is NP complete. So NP complete means problems that are NP hard as well as NP. It's the intersection of NP, NP hard and NP, which means they can be verified in polynomial time, and if they can be solved in polynomial time, if one of them can be solved in polynomial time, then everything in NP can also be solved in polynomial time. Okay? And this is one of the beautiful area within computer science. And probably many people doesn't know about this, especially math people. I don't know. I'm just at least I didn't know, or many of my friends didn't know that you can do computer science without doing any programming, and that's what exactly I'm doing now. All I'm doing is most of the time is these kind of things. It has nothing to do with computers. I don't do any programming myself. It's boring, right? But this is math and yeah. So any other questions?
Okay. Any other questions from audience side?
Yeah, somebody asked a question. If you have any questions, please leave in the chat if you don't feel comfortable to ask. You explained the K-click problem in graphs, which is not polynomial time. Yeah, K-click is not polynomial. No, so whenever I say not polynomial, we are assuming that P and NP are not the same. Okay, we still don't know whether P and NP are the same, but we believe that P and NP are not the same. Now that many smart people have tried and failed, we kind of believe that they are different. That is why we couldn't solve it. So assuming P not equal to NP, click is not in P. Okay. So in general, what are the advantages of P times solvable? For example, is there any application to the problem? The application for these kind of things are, it's almost like pure math. You don't, there is no direct application, but an indirect way of explaining an application is if we suddenly prove that something is NP complete, then we know that we are not going to solve that problem efficiently or deterministically. At that time, we can solve it using some heuristics. Okay, that is one way to say as an application, but there is no real application. From a math point of view, this is application, but from a real practical point of view, there is no real application for these kind of things. Just that we know that we can't solve it if we can't solve it perfectly, so look for plan B. And sometimes, the application is not about the solution to that specific problem. It's like the techniques or the methods we come up with, which might be applied or useful in solving some other problems, right? So oftentimes, the proof techniques are more valuable than the actual result. And these are fundamental. In computer science, what is happening is now you see there is a lot of big data stuffs and machine learnings and everything, right? And people are doing all sorts of nonsense, But everything is changing, right? It's like they do something, they get something, but after a few years, the whole thing will change. It's like a data-driven kind of things, right? I mean, they are very useful. But anything to do with these kind of things will not change even after 1,000 years, right? But machine learning, we say something today, and after 10 years, it will be irrelevant. Yeah.
Excuse me, sir. There is one question from one of the participants. Question is, which are the efficient algorithms in neural network analysis?
I mean, to be frank, I don't really know much about machine learning, and I try to stay away from it. Yeah, I don't know. I don't have a good answer to that. Yeah.
Thank you, sir.
I mean, because the thing with machine learning is it has, machine learning kind of research has gone to a stage where, see, if you look at machine learning, right, and I mean, you will see so many people with machine learning in their CV, but most of them will be doing more applied machine learning. Okay, more applied machine learning, and nowadays you don't really need to even do anything new because there are thousands of people doing things, and everything is almost like ready-made, right? And it's pretty hard to keep track of. So I don't know enough. Yeah, but to be frank, I don't know. I mostly work with theoretical stuffs. These are easy, not easy, but more clean. Yeah. But if you want a job nowadays, machine learning is a place to go.
Any more questions from audience side? Otherwise, we can wrap it up.
Yeah, and lastly, if you have more questions in the future, or if, and again, if you like to work on some of these kind of things, you can always email me, and you can have a look at my web page or DBLP. You will see some papers. If anything is interesting to you, please email me. We can chat, we can Skype, we can Zoom, and we can collaborate. Yeah, I mean, I do it all the time, and yeah.
We have yes. Okay.
And maybe I will tell this to Steve later. Maybe and maybe after next year or something. I might also have some, PhD positions if somebody wants to, come and work with me. So, yeah. Yeah, that's just for the future, if
Yes.
Yeah, otherwise I don't have, unless you have any more questions.
We have attached one feedback form also. If you have not more than question from participant side, we can conclude this. Yeah, I think we can conclude.
Sorry. Thank you, sir. I would like to express my heartfelt gratitude to Professor Sharma Thangachen for his refreshing and enlightening class on computational complexity theory, revealing the limits of algorithm.
Sir, I think she has a neck issue. That's why her sound is breaking.
It was very much informative and interactive session. This session is last but not the least, I thank you all the participants for showing their interest in the program. I once again thank everyone for making this program a success. Thank you all.
Thank you so much, Sharma sir.
Thank you, ma'am.
and we are expecting more support from your side in future also.
Yeah, definitely. You know, maybe after COVID, you know, I'll be happy to visit in person. Yeah,
Thank you,
yes.
sir.
Thank you so much, Sharma. It was a very wonderful lecture. It was.
Maybe before I stop, I just want to share one more. There is a YouTube channel which I recently find out. It's called Mind the Decisions. I will just type it there.
Okay.
1 million subscribers. So it's called Mind the Decisions. I just type there. It's a nice channel, and what they have is like lots of puzzles. It's fun. Okay, so as mathematicians, like, you know, just have a look at it, and they will give you like high school level puzzles, but sometimes it will challenge us. When we think that we might know many things, but these are like simple, you know, yeah. So yeah, something interesting. So I thought I will share it. Maybe, you know, yeah.
I think no further question. I think we can conclude. I think. Okay, thank you so much, Sharma, for your wonderful lecture in the very late night. I think time is about more than that is midnight, right?
1:30.
Oh, 1:30. Okay, it's time to sleep. Okay. Okay.
I'm driving back. I have like 20 minutes time.
Oh, okay. You are in office. Your cabin.
Yeah, I just came to my office. So
Okay. Thank you so much for that, for our coming, for our joining, for presenting our webinar. Okay, in future we will collaborate with this kind of that open webinar. Okay, then we can conclude that. Thank you so much once again. Yes. Okay.